You ever just watch water flowing from a faucet, or maybe smoke curling up from a candle? It seems so simple, doesn't it? But what if I told you that inside that simple motion, there's a hidden battle playing out, a conflict between two forces that literally shapes our world, from the weather outside to the blood flowing in your own veins? So, really, what could possibly connect that gentle, quiet rise of smoke with a chaotic, crashing stream of water? I mean, on the surface, they're total opposites, right? One is calm, the other is just wild. But they're actually two sides of the very same coin, and they reveal a fundamental secret about how our universe works.
And that secret is this right here. It's an invisible battle between order and chaos. You can almost see it happening. Smooth, perfect lines suddenly breaking apart into a swirling mess. This is the constant tug of war that happens in any fluid, a fight between predictable, orderly movement and just wild, untamed energy.
All right, so let's get into it. Let's really break down this whole order versus chaos thing. We're going to define the two fundamental states of how fluids can move. Okay, so here they are side by side. On the left, you've got laminar flow. Think smooth, streamlined, totally predictable. Everything just flows in nice parallel layers. Then, on the right, you've got turbulent flow. And well, it's exactly what it sounds like. Chaotic, irregular, with all these swirling eddies. It's completely unpredictable. They're polar opposites for sure. So for laminar flow, the best way to picture it is to imagine a highway at 3 a.m. There's no one else on the road, and all the lanes of traffic are moving perfectly. Each little particle of fluid is like a car staying in its own lane, just gliding along smoothly. There's no cutting each other off, no mixing. It's just elegant, efficient, and totally orderly. Now for turbulent flow, yeah, forget that perfect highway. This is a mosh pit at a punk rock concert. The particles are just crashing into each other, swirling around in these crazy vortices, and everything is getting mixed up. There are no lanes, there are no rules. It is pure, energetic chaos. And that mixing, that's the key thing to remember here. It's what makes turbulent flow so different. Okay, so what is it that decides what makes a fluid act like organized traffic one minute and a chaotic mosh pit the next? There's got to be some kind of switch, right? A tipping point. Well, it turns out there's a secret code that governs the whole thing, and we're about to crack it. So yeah, what is that tipping point between smooth and chaotic? I mean, this is one of the biggest questions in fluid dynamics. When does that nice, orderly flow just break down? It's not random. There's a very specific trigger. And fun fact, predicting this transition perfectly is actually one of the great unsolved problems in all of physics. And the answer, it all comes down to a single, really elegant number called the Reynolds number. You can think of it like the score in that tug of war we talked about. On one team, you've got inertial forces. That's basically the fluid's momentum trying to just go wild and cause chaos. And on the other team, you have viscous forces. That's the fluid's internal stickiness or friction, trying to keep everything nice and orderly. The Reynolds number just tells you which team is winning. And the outcome is really straightforward. If you have a low Reynolds number, it means those viscous, sticky forces are dominating. They're keeping everything in line. The result? You guessed it, smooth laminar flow. But if you get a high Reynolds number, it means the inertial forces, that momentum just completely overwhelms the viscosity. Chaos wins. And the result there? You get turbulent flow. It's that simple. Okay, so this is all great in theory, but what does it actually look like in the real world? Let's take a super practical example that engineers deal with every single day. Flow inside a pipe. This is where the rubber really meets the road for these concepts. Now, inside that pipe, if you've got laminar flow, something really cool happens with the speed. Because of something called the no-slip condition, which basically just means the fluid molecules right at the pipe wall stick to it and don't move, the velocity isn't the same everywhere. The fluid right at the walls is at a dead stop. Then the layers kind of slide over each other, getting faster and faster towards the middle. It creates this beautiful, smooth, parabolic shape, almost like a bullet, with the fastest moving fluid right smack in the center. But what about turbulent flow? Well, that mosh pit is back in full effect. All that intense mixing and swirling just averages out the speed across most of the pipe. So instead of that pointy bullet shape, you get a much blunter, almost flat velocity profile. The fluid is still stopped right at the wall, sure, but it gets up to speed way faster, giving you a much more uniform flow across the whole pipe. So, why does any of this matter? Well, this is the crucial part. The type of flow has huge real-world consequences. Laminar flow is smooth, so there's less friction. That means you lose less pressure, and it costs a lot less energy to pump it. The downside? That lack of mixing means it's awful for transferring heat. Turbulent flow is the exact opposite. All that chaos creates way more friction and costs more energy, but that incredible mixing makes it absolutely fantastic for things like cooling systems and heat exchangers.
So yeah, this is way more than just a cool physics puzzle. Being able to understand, predict, and even control this switch between order and chaos is, well, it's at the very heart of so much of modern engineering. It has massive implications for everything from efficiency to safety to design.
And seriously, once you start looking for it, you see it everywhere. If you're designing an oil pipeline, you want to keep the flow laminar to save energy. If you're engineering a pump or a turbine, you have to account for it. If you're building a flow meter to get an accurate reading, this is critical. Trying to reduce drag on a car or a plane, you're playing with this balance. Optimizing a heat exchanger to cool your computer, you actually want turbulence. It's just everywhere.
So think about it. We just saw how a single number, a simple ratio, can predict the jump from perfect order to total chaos in a fluid. It just makes you wonder, right? What other simple, elegant rules like that might be out there, just hiding in plain sight, governing all the other complex, chaotic systems that we see all around us?